Hello, hello everyone. I am Mac Ershad D. Pabilian, your host, and welcome to the first Engineering Practice Magazine webinar series about refinery overview with fuels compliance, sponsored by International Association of Certified Practicing Engineers and Engineering Practice Magazine, in collaboration with Philippine Institute of Chemical Engineers Cebu chapter. So before we start, we should observe a proper etiquette and please kindly change your name. Please turn off your audio and video during the webinar so that the speaker and your fellow participants will not be distracted. And at the end of the speaker's presentation, we shall be entertaining questions. You may type your questions through the chat box, and please do not include your full please do include your full name and affiliation so that we can address you properly. Kindly accomplish the evaluation form to be presented at the end of the webinar to receive a certificate of participation. And lastly, a link to a recorded version of this webinar will be available. So may I call on Carl Colmetz, the president of IACPE, to introduce Engineering Practice Magazine and KLM Technology.
Good morning. We're happy you're here today, and we want to thank you for attending the webinar. So we'll tell you a little bit about who we are and why we're here today. Next. 1997, we started KLM Technology Group, and we provide engineering support for the hydrocarbon processing industry. 2007, we started writing engineering design guidelines. A young engineer suggested that we write engineering design guidelines, and we started them. 2014, we renamed the engineering guidelines to the Coleman's Handbook of Process Equipment Design. Next. If you've searched anything on the web, you have found these documents. There are 100 plus engineering design guidelines on a range of topics from pumps to compressors to crude units. We've got about 7 on crude units. We got 5 or 6 on ethylene plants. And so if you've searched anything on the web, you've probably found these particular documents. Next. So I get emails from students asking for student discounts. The handbook was mostly purchased by companies, so the cost is high for students. In June of 2014, we developed an idea to start an engineering association to utilize the handbook to train and certify individuals at a student rate. Okay, so we're looking at, so basically the handbook, if you buy the chapters, is very expensive. If you join the organization, you're able to get a number of the handbooks at a lower price, training and certification. And then in April 15, we started Engineering Practice Magazine. We're now in our 6th year of publishing the magazine. Next. So we're approaching 20,000 readership per issue, which I'm very pleased and honored. We're actually rated higher than many of the name brand magazines for online readership. So if you're interested, we're looking for great technical articles. And so we're always looking in several of the following months. We're going to have people that publish in our magazine to come speak to you in a webinar. Next. So I'm very pleased at the reception from the public. Alexa is a Amazon company, and they rank readership, and it's online readership. So Engineering Practice is ranked 295. Oil and Gas Journal's higher than us. The lower the number, the better. Hydrocarbon Processing doesn't have the online readership we do. Hydrocarbon Engineering does not. So if you want to publish a magazine that's going to be read, we suggest you consider publishing an Engineering Practice magazine. Okay? And that's all I have for today. Thanks.
Thank you, Carl, for the introduction. May I call on Engineer Mark Lester Real to introduce our speaker today?
Thanks, Engineer Pabilian. So I'd like to introduce today's presenter. So our Speaker for today is a downstream petroleum professional with over 25 years of progressive experience in the operations management of refineries in the United States. Strengths encompass a strong refining background from unit operations, laboratory management, product inspection, refinery economics, tech services, and fuels regulatory compliance, with the ability to implement improvements across multiple boundaries from receiving crude to product shipments from pipeline terminals. So, ladies and gentlemen, let's welcome William Lutz.
So good evening. I'd like to start the presentation by talking about some things I've learned along the way, and some of them the hard way. I usually like to start this when I'm talking to students and young engineers because I'm hoping that some of my experience will pass on to them. Next. So one of the first things is you owe your boss your opinion once. If you have a boss that really doesn't want to listen, um, you have an ethical obligation to tell him your opinion about whatever project you're working on. After you've met this ethical obligation, your job is then to follow directions. So if you got a boss that wants to listen to you and is happy to do so, you can tell him more than once, but you owe him the one time no matter what. Now, the exception for not going into this more in depth is safety issues. If you're working on a project, you see a safety issue, once it may not be enough. You may have to tell him until you get it across that there's really a safety issue here. And that is to the extent for me that if I think there's an unsafe project and they're continuing on with it, I'm going to object so much that I'm willing to lose my job. Next. Okay, so the next thing is you've got to realize that your boss has a bigger window on the project than you do. You've got a certain size that you're looking at, but your boss has a bigger view. He's talking to people above him and around him and outside people and that sort of thing. And so if you give him an opinion, he may agree with that position. But if he's been instructed to move in a different direction, he's not necessarily going to follow your advice. Next. The next thing is don't hide mistakes from your boss. Most mistakes will be discovered. It'll be better for you to be honest up front. And if you are honest and you have a good boss, he'll help you resolve the problem and he'll kind of take care of you. But if his boss finds out before he does, you're going to be in big trouble. Next. Okay, next thing. You work for your boss. Your coworkers do not work for you. They work with you. Treat them as if they are doing you a favor if they help you. Next. And then always give the credit away. If you get credit for a job, give it to other people. Your boss and his boss will really understand that the credit for a project that you're working on belongs to you. And if you give credit to all those who helped you, not only will they be more willing to help you in the future, but your boss will understand that you're a good team leader. And if you give credit to those outside of your department or company, your boss will understand that you can influence others that don't report to you or him. Next. So you're going to be working with people with different backgrounds. All projects in a refinery usually encompass a lot of different professionals. If you're leading the circus act and all of you do the same thing, it's not going to be a very good circus. You will need to know a certain about each different job that you're leading. And this is how you're going to effectively lead this. Now, one of the things I've always thought about is that if you are an engineer and you're working with an accountant, and you learn a little bit about his job so that you can kind of direct him properly, when he goes to speak to other accountants about you, he's going to say, you know, he's the smartest engineer I've ever met. Next. Okay, so now we're going to get into the regular presentation. So refining in the petroleum industry is the conversion of crude petroleum into useful products. Each refinery uses different processes depending on the feed, the products, and the equipment. Next. So these are some of the products, and we're going to kind of go down from light to heavy. So you're going to, on the top, you're going to have your fuel gases and liquefied gases. These are going to be your fuel or chemical feedstock. Often these fuels are actually used to fire heaters further down the line in the refining process. Gasoline, we know what that is. In some of the countries, they call it benzene. So, and that's pretty easy to understand. It's for gasoline and such. I mean, for cars and such. You're going to have naphtha, which is a chemical feedstock. It can also be blended into gasoline. And then you're going to have jet fuel or kero, which is aviation fuel. Kerosene used to be used in lamps, and now it's typically used to power jet engines. Your diesel fuels, that's going to be for your motor, railroad, and marine. And then heavy fuel oils will be for marine and industrial fuel. And then lubricating oils, that's kind of obvious. White oils will be your electrical insulation, lubrication, and pharmaceuticals. Waxes, polishes, pharmaceuticals again. Bitumen or asphalt, as we call it, is basically for road making and waterproofing. And then your petroleum coke that comes off the bottom is going to be either go to fuel or it'll be used in electrodes for metal manufacture. Next. Okay, so there's different categories of refining, and they're going to be either a fuels refinery, they make coke, lubricants, or petrochemicals. Now, it can be one of these, it can be a combination of these, it can be all of them. Some of the refineries I worked with were strictly fuels. One was fuels and petrochemical, one was fuels and coke, and one did all of the above. Next. So we're going to talk about feed. Your crude oil is basically going to be broken down into two major categories. You're going to have a light crude oil, which is generally low sulfur, and you're going to have a heavy crude oil, which is generally high sulfur. Next. So this is one I'll get into a little more about. You're going to have, this is the crude coming into the refinery, how it's broken down. And it'll come in at the atmospheric tower. You can, it'll go across the top. You have your light ends, which will be your plant gases, which I had mentioned earlier, fuel heaters and stuff downstream. And it can also go into light straight run gasoline. You're going to have your naphthas. This again will go into chemicals or gasoline. Once we get into this stage, we're going to start hydrotreating. Typically, hydrotreaters can be anywhere in the cycle. They may locate them before the crude units, after the crude units, after the products, different places. But in this instance, we're going to hydrotreat most of the products coming off the atmospheric tower. And then they'll go into different units downstream. So in the case of naphtha, it'll go into a cat reformer. The CMS. This is kind of an unusual stream. Sometimes refineries will have this draw off of the atmospheric tower. Most of the time they don't. And to give you a little bit of an idea about that is that one of the knobs, as we call it, the ability to adjust things on these towers is we can change the temperatures and either increase or decrease how much we want to pull for each one of these. So if we don't want CMS, we can push the upper parts of that into the naphtha, we can push the lower parts of that into the kerosene, and so forth down the line. And this gives us control to meet the requirements of the marketplace. So if there's no demand for jet fuel right now, which is pretty low, we're going to push the upper end of that up into products above, and we're going to take the lower end of that kerosene and we're going to push it down into the diesel. So that's just an idea of some of the things we can do. Almost everything on here we can adjust. So the bottom of the atmospheric tower is going to go to a vacuum tower. And here we're going to typically pull out vacuum gas oil. So we're going to have a light and a heavy, and they'll be hydrotreated. And they typically go to an FCC unit, which is a fluidic catalytic cracker. This will take and break these down into more usable products. And then the FCC will further send stuff to the alkalization unit and gasoline blending, or it could go into light cycle oil, which can go into your diesel again. And then you'll notice back at this area around the bottom of the atmospheric tower down to the DAO tower, which is the de-asphalting oil tower. These are kind of connected. And so we can kind of move these around. We can push them down to go to the coker if we needed to, or we can push them through the FCC area. And then once we get down to the DAO tower, we can go to the coker, or we can basically take the bottoms off, and that'll be asphalt or fuel oil. Okay, next. Okay, so this is kind of an overview. You're going to have crudes coming into the refinery. These could be either brought in domestically by pipeline or trucks, or if it's imported by ship, they'll go through pumping stations. They'll go to the refineries where they'll be produced into products. Also, we will import and export products downstream of the refinery for blending. If we're not making enough diesel or enough gasoline, we can move those products in and out. So a good idea is typically Europe likes to use a lot of diesel right now, and the U.S. tends to use more gasoline. So downstream of the refinery, we'll bring in gasoline from Europe and we'll export diesel to Europe. And so then that'll go into the blending, and then it'll go out pipeline, and then that'll be what's distributed downstream to your aviation, your gas stations, and all that. Next. Yeah. Okay, so let's go back to crude oil a little bit. And crude oil is a mixture of greater than 10 to the 8th power of compounds. And that's a lot of different compounds. And obviously, if you've got that kind of a number, most of them are going to be low in concentration. And so what we typically do is, instead of trying to understand every compound that's in the crude oil, we try to measure the crude oil by bulk properties instead. Next. Okay, so the first one and the most common thing we use is the API gravity. And the reason this is interesting is needed by us is because The gravity or the specific gravity is going to be how we measure the volume. And so it's important to know what the API gravity is for this purpose. One of the common things that we use in the United States is API gravity. And in the rest of the world, they use specific gravity or relative density. There's a formula here for converting. Typical gravities, or water is going to be 1.0 for specific, but it's going to be a 10 API gravity. And the way the gravities work is API and specific gravity kind of work inversely. So as the product gets heavier, the specific gravity goes up, and as API gravity goes up, the property gets lighter. So water is a 1, the API is a 10, gasoline is a 0.74, whereas it's a 60 API, and these are approximate. Next. Okay, so the next thing we're going to talk about, and this is one of the most important parts, especially in the environmental situation today, sulfur content is really looked at greatly. And we measure that in weight percent. So it varies from less than 0.1% to greater than 5%. So high sulfur crudes, which we call sour, are typically greater than 2.5% sulfur. And low sulfur crudes, which we call sweet, are typically less than 0.5%. Next. Other properties are found by standard analysis procedures. So it depends on what country you're in and what the standards are for them. But generally, we use in the US API or ASTM. And things that we look at are pour point, salt content, crude oil assays, metal content, and there's some other things too, but these are the majors. These will give you some indication as how easy it is to process the oil, and it also plays a role in pricing. Next. So the first one we'll talk about is a pour point, and that's the ability of liquid to flow at low temperatures. Pour points are typically, they're designed to be rated at 5% higher, 5 degrees higher than the temperature at which the liquid stops flowing. And crude oil is typically a minus 50 degrees Fahrenheit or minus 46 degrees centigrade. For crude oil, it's a rough measurement of the relative amounts of alkane and aromatic compounds. The lower the pour point, the lower the alkane content, and the greater the aromatic content. It also, if you have real high paraffinic crudes, it can raise the pour point considerably. There were tales of the Japanese during World War II in Indonesia. The pour point was so high on the crude oil that they could pump it into wicker baskets and float it down the river downstream, and that's how they brought it into the refineries. Next. Salt in crude oil is the form of dissolved or suspended salt crystals in water, and it's emulsified with the crude oil. We're tending to desalt to lower concentrations as much as possible. If the salt isn't removed, it causes fouling and corrosion problems, and so we remove that by extraction with water. Next. Metal contents are important. Crudes can be from a few parts per million to more than 1,000. Certain metals, nickel, vanadium, and copper, can deteriorate catalyst activities and processing. So you don't want to burn up your catalyst. So you want to make sure you pull these metals out. The metal content may be reduced by solvent extraction. Next. So in addition to measuring the bulk properties, crude oil is also characterized by boiling point fractions. So each fraction can then be analyzed for the same properties and for appropriate product properties. To give you an idea here, we're going to basically run in a flask what the crude tower does that I mentioned earlier. And we're going to take those runs and then we can further analyze those to see what the crude is going to produce when it goes through the refining process. Next. So this is kind of an example of that. We've got basically a flask over here. We're going to heat the crude oil up and we're going to watch the temperature as the percent of feed comes over, the product comes over into the receiver. And we'll do this slowly so that we can get an idea of the breakdown of temperature 2% recovered. Next. So the first fraction typically boils at less than 40 degrees. And this is going to be your LPGs, your light ends. Next. The second fraction is going to be between 40 and 90 degrees. And this is going to be your light naphthas. This can typically be blended into gasoline or upgraded into a higher octane gasoline downstream. Next. So then at 90 to 190 degrees, we're going to get our heavy naphthas, same thing. We're going to look at this, bring it over, see what the percentages are, and then we'll know how much of this crude is gasoline. Interestingly enough, when the U.S. started fracking, before that, we were all running heavy sour crudes. And then when we started fracking, we started getting into light, sweet crudes. And when that happened, we ended up getting a lot of these naphthas in the crude, more than what we would normally get with a heavy crude. And so it would cause problems with overloading the refinery with C5s. And we had a hard time doing that. So that's when they started allowing us to export. And now we blend crudes so that we can get what we want through the refining process. Next. So the next cut between 190 and 270 is kerosene. And kerosene is generally what we make jet fuel out of. And like I say, we can do different things. We can take the upper part of that and we can push it up into heavy naphtha, and we can take the lower parts and push that out down into diesel again, so that we can adjust our output. Right now, we're trying to minimize kerosene, but when the travel industry picks it back up and we're flying a lot more jets, that'll go back into effect again, and we'll start pulling more kero. Next. I think we ended up with the same one there. Okay. All right, so after kerosene, we're going to get our gas oil and diesels. These are going to be at a higher temperature coming across. This will go into diesel fuel and heating oil, and of course, it'll be hydrotreated, and then it may be blended with diesel from other units that are going to pick up the fuel in other places. Next. Okay, and then when we get to pretty high temperatures, we're going to start getting the vacuum gas oil. These are the ones that on the atmospheric tower is going to be really heavy, and we're going to push that into a different tower, which, as I mentioned earlier, the vacuum tower. And what we do there is that by pulling a vacuum on the tower, or in this instance, our little still that we're testing, we can lower the temperature that the product actually boils at. As you know, if you lower the if you lower the pressure, stuff will tend to boil faster. So your vacuum gas oils are going to be a pretty good chunk of the crude in most instances. Next. Okay, the oil always contains a fraction that can't be distilled, and this is known as the residue. And the residues can be used to make asphalt or coke, or they can be converted into lighter products and into heavy fuel oil. Next. Okay, so now we're going to get into fuels a little more in detail. Almost all refineries produce gasoline, jet fuel, and diesel. And those are probably the ones that you're going to be most familiar with. So let's take a look at these in more detail. Next. Okay, so let's talk about gasoline first. And gasoline is not the natural or straight run gasoline that comes off the atmospheric distillation tower. That will go into gasoline production, but we're getting a lot of upgraded gasolines from other units that we blend to make the final specifications. And these streams can include gasoline off of the FCC, which we call cat gas, gasoline that comes off of the coker, alkylate, which is an upgrading of the octane that comes off of the gas that comes off of the FCC. Reformate, butane, and oxygenates can all go into blending gasoline. Next. So governments usually set standards to specify the octane, the RVP, and the sulfur content. And these are the majors. This is what people are looking at the most. But they're also looking at aromatic content, olefins, which are alkenes, and they're looking at oxygenate content. And they look at, and even though benzene is an aromatic, they're looking at benzene content specifically because it's a carcinogen. Next. Okay, so the first problem that the refining industry ran into is that the straight run gasoline that came off of the crude units had a low octane number, and it would cause the cars or the engines to make what we call knocking sound. And so the refineries have been working to improve this over the years, and now we've found that the best octane index is generally in the range of 87 to 93. One thing you need to know is that the octane rating is just that. It's a rating. It's not any percent or amount of octane that's in the gasoline, isooctane or normal octane. It really doesn't have anything to do with that. The isooctane is basically a comparator. And so we will run that with a mixture of normal heptane to set a standard. And then we run the gasoline against the standard to see what the knock is. Next. So octane is actually a measure of the resistance of the fuel to igniting early in the combustion cycle of an engine. So what typically happens is when the fuel goes to the cylinder to ignite in the compression cycle, it's supposed to be for gasoline ignited by the spark plug. But if you have a low octane fuel, it will ignite early. It'll ignite quickly. And so what happens is that it ignites before the piston gets into the right position so that it can be ignited by the spark plug. And when this happens, it causes this knocking, and it's the engine firing too soon. Octane requirements are based on the compression needs of the engine. The higher the compression, the more the need to inhibit the early ignition. So if you have a high compression engine, you need a higher octane fuel. Now, octane in excess of what the engine calls for does not really create any added benefit. So if you just have some extra money in your pocket and you decide, oh, I'm going to treat my car or my motorcycle or whatever to a higher octane fuel, and it's higher than what the engine specifies, you're kind of wasting your money because the engine's just going to use what it uses. And if you have a higher octane above that, you're really not going to get any benefit out of it. Next. So there's two types of octane numbers. One's called the RON, which is the research number, and the other is called the MON, which is the motor octane number. And the difference between these two is that the engine is run under different conditions to generate these numbers. So your RON is basically approximating city driving, and the MON is approximating highway driving. Next. So some governments, US, rate the octane as the average of the RON and the MON. So the average posted at the pumps is the RON plus MON divided by 2. In some countries, only the RON is posted, with some posting the sensitivity, which is defined as the difference between the RON and the MON. Now, the RON typically runs at a higher number than the MON. And so if you go to Europe and they're only posting the RON, you'll see a 98 or a 99 or whatever octane. And in the US, you'll see a lower octane number, but that doesn't necessarily mean it's a lower octane fuel because it's measured differently. Next. Then the next most important property is volatility. And volatility is the ability for the gasoline to vaporize. So if the volatility is too low, the engine won't start. The gasoline won't turn into a gas because it's not the liquid that explodes in the combustion chamber, it's the gas. If it's too high, then what happens is that you'll get vapors forming in the fuel lines or the fuel pump or whatever, and it'll cause the fuel not to flow through those lines, and that's called vapor lock. Next. So we measure the volatility by the vapor pressure, and the vapor pressure is measured at 100 degrees. We use what's called the Reid vapor pressure method, and you'll see the vapor pressure listed as RVP. The old method, which was with bombs and gauges, was ASTM D323. The new method that you'll see quoted most frequently now for vapor pressure is ASTM D5191, which is basically a box that you plug some sample into and push a button and you get a number. The RVP might need to vary from summer to winter. So if you're in a climate, if you're in an area where the climate doesn't change much, you won't see much difference in the vapor pressure. It'll be pretty constant. But if you're in a northern or southern, very southern latitude where it gets cold, then we need to adjust this RVP for summer and winter use. And they can range from 49.6 to 93.1 kPa, which translates to me in PSI, which I'm used to using, at 6.8 to 13.5 pounds. In extreme cold weather climates, this can be as high as 15 psi. So if you're way up north in the wintertime, you need that vaporizing to get the engine started. Usually summer gasoline is what's critical. In the U.S., we have requirements for the gasoline during the wintertime, but the EPA is really only interested in the summer gasoline. And so we're required to keep that at about 7.8 to 9 pounds, depending on the region. Next. So these are some typical read vapor pressures. So like I said, we're going to be blending a lot of products to make our gasoline. And we're going to be using butanes, we'll be using naphthas, and they have different vapor pressures, and we will blend this in such a way as to get what we're looking for. Butanes are what we use to bring the vapor pressure up with if it's kind of low. And we generally only do this in the wintertime. And so we actually have what's called a butane shuttle. And what we do is we have these underground caverns, and we will produce butane in the summertime and ship it to the caverns. And then in the wintertime, we'll bring those from and they're also called salt domes. We'll bring it back from the salt domes and then put it into the gasoline to blend it up. Next. So kerosene was originally lamp oil, and some of you may have seen it used as lamp oil. But now the biggest use of it is for jet engines. Don't get confused and think because it's jet fuel, it's going to make your car go really fast, because it's not. It's going to make it want to slow down really quickly. It's a heavy fuel, and it won't ignite in your car, in the engine. So you don't want to be doing that. Next. Okay, so some of the properties that we look at in kerosene is going to be the aromatics, the flash point. Most of the time when we run flash point on stuff, it's for safety reasons. We want to keep the flash point on products that we can, like kerosene and diesel, above 100 degrees Fahrenheit. Which is way above room temperature, so that if somebody's just handling it, it won't burst into flames. We also look at the density, which is the gravity. We'll look at viscosity, which is the thickness of the oil. And we worry about that because if it's going through lines to jet engines, we don't want it to be too thick so that it doesn't flow well. We look at what kind of carbon residue is left after it's burned. We'll look at the pour point, the smoke point, and the freeze point. Next. And these are just some specifications for these products. And it just depends on how it's being used, but typically some ideas. The flash point is going to be a maximum of 38, again, for safety reasons. The freeze point is going to be less than 40 degrees below zero. And the reason for that is that this is going to be used in jet airplanes, and they're going to be flying at 35,000 feet, and the temperature is going to be well below zero. Again, the viscosity we're going to look at because we don't want the lines to plug. And then we're going to look at the smoke point, and that is when the fuel burns, how much is not being burned properly, and that helps us understand how pure the fuel is. Next. So then we can get into diesels, and diesel is different than gasoline, and the reason is that gasoline is ignited by a spark plug in the engine, whereas diesel is ignited by the compression itself. So what we do is we're looking at a cetane which is whether the higher the number, the easier it is for the fuel to ignite, and the lower number, the harder it is for it to ignite, or a longer delay. The long delays cause misfiring, poor engine performance, smoky exhaust, and difficult starting in cold weather. However, the good thing about a low cetane number is that typically it has more BTUs per gallon and therefore more energy. And so it's better used in really heavy equipment. So bulldozers and cranes, they all operate better on these lower cetane numbers. But automobiles in Europe typically use a lot of diesel, and they want those to be a higher cetane number because they're easier to start, they produce less pollution, etc. Next. So now, like I said at the beginning of the presentation, sulfur is one of the most important things about the fuel and it being environmentally correct. So sulfur levels in diesels are continually being reduced. Back in the 1980s, diesel might have 5,000 ppm of sulfur. In 1990, we came out with low sulfur diesel, and then we came up with what's called ultra low sulfur diesel now. So current specifications in the US are about 15 ppm. What comes out of the refinery is typically about 10, but they're given some allowance in there because they push products through pipelines, and they can pick up sulfur from whatever was pushed in front of it, and so that gives a little room. In Europe, the specification is 10 ppm, and so they're trying to get a little more strict on the sulfur. However, like I said, the refineries are typically making about 10 ppm anyway. And one of the big things is the U.S. typically will send diesel to Europe, and so we need to meet their specs. Next. Okay, so other diesel properties. The volatility, is making it easier to start. The pour point. One of the reasons the pour point's important in diesel is that if you get up north, the diesel can actually set up in the lines and the engine will stop running because it can't get the fuel. And so typically what happens there is that pour point is set at 10 degrees below what the expected lowest temperature is. Cloud point, this is basically the beginning of the freeze point. So crystals start forming in the fuel, and we want to know that we're getting ready to have a problem. Gravity, this depends on where it is. It's typically between 30 and 40. To give you a rough idea about this, back in the 70s and 80s, early 80s, the minimum gravity for diesel used to be 32 in the US. And they changed it in the 80s and they lowered it to about 30. And so instead of targeting and producing diesel that was, say, between 32 and a half to 34 or something like that API, we then started trying to get it to 30 to 31 API. And as this happened, you're increasing the density, which means that you're also increasing the BTU content of the fuel. And I had a diesel car back then, and I actually started getting better mileage because the fuel got heavier. Next. So we talked about viscosity. Diesel is the same thing. It can be, we worry about it plugging up lines if it gets too viscous. And the flash point is the same thing. We're kind of worried about the flash point because we don't want people to accidentally get burned by the diesel fuel. Next. So the diesel fuel, not as much as gasoline, but it is produced by blending from various process streams. And then similar correlations are used to predict the blend properties and fix the production levels of the blend components. So like I say earlier, we can adjust the streams that come off of the units by either pushing more over the top or taking more off the bottom and pushing it down to a lower level. And we can use that, all these things as levers or buttons, as we like to call them, to adjust our flow so that we have the right amount to market. Next. Okay, so that pretty much covers the basics of a refinery. We didn't get into all the process units and all that, but the lower units, but we got into the basics, and we talked about the basic fuel properties and what we have to watch out for. Thanks.
Very informative presentation. I think we are now ready for the Q&A portion. Questions in the chat box. Engineer Jan Barbosa will read the questions for you.
Okay, so good evening, everyone. Thank you for attending this webinar, and thank you, William, for sharing your knowledge on petroleum refining. And I have a couple of questions here. So the first question is, what is the future of refining, and how long will there be crude units?
Well, obviously there's a lot going on with the environment, and we're trying to go to renewable fuels. So there'll be less in the future of refining capabilities, but we'll still be there because we'll use a lot of it for chemicals, and there'll still be some fuel needs for other things as well.
Okay, Phil, thank you for answering that question. The next question will be, what is a good field for a young engineer to enter?
Well, chemical engineering is always a good field, but the refining industry may not be a real long-term solution. One of the things going on now is obviously like the coronavirus. And so while other scientists are going to be developing the vaccines, this stuff is going to have to be produced and distributed, and that's where chemical engineering will come in. So biotech is probably going to be a good field to be into, and then other chemical processing can also be good.
The future is going to look good, where the knowledge that you learn as an engineer, mechanical, civil, chemical engineer, will be used in many areas. So we need to, I think engineering is a good field. If you want to go into, I think it's important, particularly overseas, for you to get an advanced degree. And so, you need to look at continuing your education. Okay.
Okay, so thank you again for answering that question. And now we have a question from Dev Prakash Shukla. whether there is any catalyst in which is moisture is resistant in light naphtha isomer unit.
Currently in light naphtha isomer units, we're mute your mic. Thank you. Currently in light isom units, we have dryers to remove the moisture. I'm sure there's some research going on to look at a more friendly unit, more friendly towards moisture. Currently, right now, where most of the isom units are actually have dryers in front, and so send me an email, and I'll look at some. I'll try to ask some of the Catalyst people about what is the current research that's being done on isomer units. Good question.
Okay, so thank you, Art, for answering the question. The next will be why does benzene need to be low in gasoline?
Okay, well, benzene is a known carcinogen. And so that's the reason governments are pushing to get it down. Obviously, in some countries, the name for gasoline at the pump is actually benzene, but benzene is kept at a really low level in the gasoline for these reasons.
Basically, um, the so we know it causes leukemia, and me and Bill had a whole group of friends that had leukemia in their families, and they all died about 45. Me and Bill started working together in 1979 in a refinery, and we lost a whole group of friends that died from leukemia about 45 years old. So we know benzene causes leukemia. Uh, the challenge of Asia is that benzene can be as high as 1% still in Asia. So whenever you're pumping gas or you're dealing with gas and there's leukemia tendency in your family, you may want to restrict your access to gasoline. Good question. I see some on the chat.
Yes, yes. The next question comes from our anonymous attendee. So, is there any refinery running in world co-processing biofuels with crude?
Typically, uh, biofuels can be put into charges that go into the towers, but there's some other issues with biofuels that have to be looked at. And so typically they're processed on their own and then blended into fuel downstream.
Okay, so thank you again, Carl. Next, we have another question from Muhammad Aliu. How is the alkylation unit positively impacting the refining industry?
Well, I can start off on that a little bit. Alkalization is basically taking some streams off of the FCC unit that really are kind of low octane and not great for blending into gasoline and upgrading the octane content. So it makes a real good blending into gasoline.
So what an alkylation unit does, it takes two of these C4s and blends them together to make a C8. All right. So in the summer, we can't use very many C4s. And so we want to, and it makes a C8, which is high in octane, and it's also very low in sulfur. So it's a really good gasoline blending stock. So an alkylation unit is a very good piece for gasoline blending. You got a comment on the chat box from Gareth Green, who says that UOP power isom catalyst is less sensitive to water. So that was thanks for that comment.
Okay, so the last question, has there been any new technology with regards to the refining industry that is currently implemented by big companies right now that you are familiar of?
Okay, I'm sorry. I had a hard time understanding that question. Could you repeat that one more time?
Has there been any technology or new process that had been developed in the refining industry that you currently know, recently know of right now?
I'll
I don't
let
know.
Carl
I
go
don't
on
know
to
of
that.
any new ones. I think what we're doing mostly is we're improving the existing ones, like the hydrotreaters. The catalyst is being improved. The FCC, the catalyst is being improved. Uh, we're improving the environmental. We're improving the environmental piece a lot. And so in the U.S., we're going away from any flaring at all. So there's a lot of environmental. There's a lot of there's a lot of technologies that are coming about for environmental. There's a lot of technologies uh, in ethylene. There's several new technologies that are being developed. But refining, uh, I don't I don't know of any. Of course, there's probably research being done. Okay.
So I think we will just go ahead with this last question from Vinod Raj. Where can we use the sulfur as nowadays more stringent with sulfur in gasoline and in diesel? Is there any demand for sulfur?
Okay. Very good. So you got the octane piece. You've also got the sulfur piece. Currently, they're taking the sulfur and they're making it back to elemental sulfur, which is yellow sulfur, and it's sold into pharmaceuticals, medicines. So the sulfur is actually sold into a lot of pharmaceutical companies. So a lot of medicines have sulfur compounds. So a big portion of the sulfur is sold into medicines.
Okay, so I guess that wraps up our question and answer portion. I will return the stage to Erstrad Pavilion. Tabs?
Okay. Wait. I think we have a last question about the what is the procedure for writing articles in Engineering Practice magazine. Uh,
What
yeah.
we're looking for good technical articles. So you can submit an article to us, and we'd be very happy to review that article, and would have our team look at the article. If they're happy with it, we'll publish it. But it's basically just needs to be a good technical article. How did you learn to walk? How did you learn to walk? Well, you fell down a few times and then you got better. How are you going to learn to write good technical articles? Well, you're going to have to start writing. All right. And so I would encourage you to write them, send them in. I'll give you comments back. Okay, do this, do this, do this. And so, and then at some point, uh, if you're a senior guy, he's probably gonna be accepted. If you're a younger guy, I'm gonna go back with comments and say, okay, include this, and then we'll probably end up publishing.
So that ends our question and our answer portion. Thank you, Sir Carl. And on behalf,
Okay, so looks like Pavilion had technical difficulty. I will take over from this uh, point. So that ends our webinar and our question and answer portion. So on behalf of the IACPE and Engineering Practice Magazine, I would like to present the Certificate of Appreciation to William Watts for sharing his valuable knowledge and expertise. And before we leave this meeting, kindly fill up the evaluation form for this webinar session located at the chat box. For this will be the basis of those who will receive the certificate of attendance, a link for the recorded version of this webinar as well. So thank you everyone and see you in the next few weeks for our next webinar session.
The next webinar Next webinar, we'll look at distillation troubleshooting. In February, we'll probably look at another refining in March, and maybe look at compressors in April. So we're looking at having one a month.
So thank you, everyone. Thank you for coming. See you in the next few weeks.
Thanks, guys.